Hi, my name is Stephanie Brinkerhoff, and thank you for joining me today. I have 12 years experience in commercial, residential, and petrochemical manufacturing. So we'll be moving through some project management aspects today, archetypes, and how that evolves into technology that we're going to use, AI technology specifically in this sector. So no matter what field that you're from, you'll be able to apply a lot of these aspects and technologies to what you're currently doing. I have also left my email at the bottom. I hold a master's in legal studies from Cornell University and several project management certificates. I think that's it. So this analysis employs the SWOT framework of strengths, weaknesses, opportunities, and threats to comprehensively assess the impact of AI in these studied critical domains. By examining the current state and future prospects, this analysis shed light on AI implementation's potential benefits and challenges, aiding policymakers and stakeholders in making informed decisions to harness this potential for positive societal outcomes. By leveraging strengths and opportunities while addressing weaknesses and threats, stakeholders can make well-informed decisions to foster AI's responsible and beneficial integration in these critical domains. As environmental pressures on energy sources increase, it comes as no surprise that renewable energies such as hydrogen fuels and carbon capture technology are gaining prominence in energy grids due to the human desire for better energy control. The growth of renewable energy is evident, and the key challenge lies in effectively managing it to meet the global demand for clean and affordable energy. Consumers, producers, and governments emphasize the importance of cost effectiveness and environmental considerations. In this context, solutions must be sought, and AI emerges as a significant opportunity to address the current needs of societies. The widespread implementation of AI offers several advantages, including high speed predictions and generalizations, flexibility, explanatory capabilities, and symbolic reasoning, which can significantly contribute to overcoming challenges. AI plays a crucial role in the energy sector, mainly due to its ability to handle vast amounts of data and navigate through the growing complexities of the energy system. Within the renewable energy sector, AI can significantly enhance various aspects, including improved monitoring, efficient exploitation, enhanced maintenance, and optimized energy storage solutions, just like carbon capture technology. Additionally, AI facilitates the implementation of timely operation and control systems, which we already are seeing in the energy sector now. Okay, we can go to the next slide. Take a moment to familiarize yourself with figure one. You'll see at the bottom a list of project management aspects that you have used one or all of at some point in decision making as a leader. Even if you're not in the energy sector, you use these aspects daily in your respective field. You should begin to notice a pattern here, where AI scores higher and where it does not. Where you see AI support the most is project information management, budgeting, and project risk management. This analysis shows that using AI technology for projects is particularly effective for complex projects involving AI analyzing large amounts of data for decision making. So, with access to unlimited information to power rapid learning capability and no emotional constraints, AI excels in assisting projects in this capacity. Just because AI can master many complex aspects, it does not mean that leaders are at risk of being replaced. We as humans want to innately be led by other humans. Even if that human comes with flaws and messiness, we accept it. In an AI future, project managers who leverage AI will have a distinct advantage over productivity, efficiency, and decision making at the same time. Leaders who exhibit more human centered leadership will excel at attracting, developing, and motivating top talent. So, how does one know whether to leverage AI or bring human qualities to a situation or combination of both? Ask yourself this question. Does a situation rely on knowledge, rational thinking, or analysis? Or does a situation require social and emotional decision-making skills? You can go to the next slide, and there's actually a video, so you'll need to turn on the volume for this one. We can go. Technology plays a critical role in the petrochemical industry, enhancing efficiency, safety, and sustainability across various stages of the petrochemical process. Here are some key areas where that technology is used. Exploration and production. Advanced seismic imaging technologies such as 3D and 4D seismic surveys help locate oil and gas reserves by mapping subsurface structures. Innovations like directional drilling and hydraulic fracturing or fracking improve the precision and efficiency of extracting hydrocarbons. Real-time data collection and remote monitoring systems allow for better control and optimization of drilling operations. Catalysts are used to speed up chemical reactions in refining processes, such as cracking and reforming, to produce valuable petrochemical products. Advanced distillation technologies, including fractional distillation and membrane separation, help separate and purify different components of crude oil. Automated control systems monitor and adjust operational parameters to maintain optimal conditions in refining processes. Next slide. Manufacturing and production. Technologies like high-pressure polymerization and metallocene catalysis are used to produce various polymers such as polyethylene and polypropylene with specific properties. Computational tools simulate chemical processes and optimize production parameters, leading to more efficient and cost-effective manufacturing. Safety and environmental management. Advanced sensors and monitoring systems detect leaks of volatile organic compounds and other pollutants, ensuring timely repairs and reducing environmental impact. Technologies like satellite imaging and air quality sensors monitor emissions and environmental impact, helping to ensure regulatory compliance. Next slide. Energy efficiency and sustainability. These systems optimize energy use across various operations, reducing costs and minimizing the carbon footprint. Technologies capture and reuse waste heat from industrial processes to improve energy efficiency and reduce environmental impact. Data analytics and artificial intelligence are used to analyze large amounts of data for predictive maintenance, process optimization, and improved decision-making. Virtual models of physical assets and processes, or digital twins, help simulate and analyze operational scenarios to improve performance and reduce downtime. Next slide. So here are two examples of visual archetypes, or what I would even call a chart used to map out a project. On the left is a sprint burn down chart, and on the right is a project journal. And there are many out there. I'm just using these two for this presentation for this purpose. Software projects rely on archetypes like pre-existing mental images of how projects work. They guide distribution of responsibilities, planning, or expectations. However, with technological progress, these archetypes may become outdated, ineffective, or counterproductive by impeding more adequate approaches. They may not apply to what you're working on anymore. So they evolve with technological advancements, such as the way a petrochemical product is fabricated or a hydrogen fuel technology advances. Software development is core to leveraging the development of applications using machine learning and AI. Development of applications using existing machine learning and AI need to be questioned, adapted, or even replaced. It can inform future development projects based on AI development platforms. Project leaders should proactively manage project archetypes, while researchers should investigate what guides initial understanding of software projects. Next slide. This is a model of an RCNN chart, which is a region-based convolutional neural network. It is a type of deep learning architecture that is used for object detection and computer vision tasks. So if you think about how you're going to map out building a carbon capture reactor or a seismic drilling sensor or any other large-scale project, this is where we're going to break down how that process and programming works and bring it to life. RCNN was one of the pioneer models that helped advance the object detection field by combining the power of convolutional neural network region-based approaches. In the first stage, a non-neural algorithm scans an image and identifies regions that may contain objects. In stage 2, the feature extractor uses resized regions to generate classification information for each region. So a classification head predicts the class probabilities for each project. And you will notice classification layers, progression layers, and the bounding box refinement layer. RCNN's impact on the field of object detection is still felt today, even though it was developed in 2014. And it has now been replaced by more powerful algorithms. This process demonstrates the importance of supervised pre-training and domain-specific fine-tuning, as well as the power of using CNNs to extract feature representations of images. We can go to the next slide. The deep learning-based approach presented in the above study here was built on RCNN modeling, so we're going to kind of jump off of that. Mask RCNN, or mask region-based convolutional neural network, is a deep learning model that combines object detection and instance segmentation. It's an extension of the faster RCNN architecture. Mask RCNN's key innovation is its ability to perform pixel-wise instance segmentation alongside object detection. So it can differentiate individual instances of objects, outline their boundaries accurately, and provide a pixel-level understanding of objects within an image. Mask RCNN can accommodate multiple classes of overlapping objects. The neural network of the mask RCNN model is built with different hyperparameters. The hyperparameters can be fine-tuned depending on the requirement of training efficiency and model accuracy for optimization. So programmers generally conduct many experiments to determine the optimum learning rate and accuracy of the model. Next slide. Project Assistant stands for Learning and Robust Decision Support Systems for Agile Manufacturing Environments. Assistant is focused on the development of AI-based tools that capture and streamline the workload of adaptive manufacturing environments. In particular, Assistant will design and develop a set of digital twins, AI systems that incorporate manufacturing domain knowledge and utilize machine learning optimization that allow data scientists and external end users to embed domain knowledge in and use the twins without a detailed understanding of the underlying system. So very user-friendly. The assistant tools are aimed to facilitate integration of complex manufacturing systems with diverse data sets into a singular logical system for automation, and operation of complex collaborative production systems that can be dynamically reconfigured on demand. AI technologies are extensively used today for automation and learning in the delivery of digital services. So, for example, in cloud computing, such as Google, Facebook, and Amazon, however, while these services are commercially successful and scalable and widely applicable in conventional environments, parts of underlying business models are based on harnessing the economy of scale efforts of massive data centers. So this is not directly transferable to manufacturing. Certain AI-related technologies have long been adapted and developed for manufacturing, automated machine tuning, and predictive quality inspection. But manufacturing AI tends to be applied at fine-grained decision-making levels, which makes it hard to scale these efforts. So to extend the capabilities of manufacturing AI systems and make them more applicable in broader scenarios, Assistant employs a combination of predictive and prescriptive analytic techniques to embed AI production, planning, and scheduling. To retain human control and system accountability, Assistant develops a generative design framework for optimal interaction between human decision-making and AI-based decision support. This last figure is a visual representation of the tools and steps required to realize our vision and where we're going to bring it all to life. The framework requires the following components: a definition of ethical by design architecture, data fabric leading into real-time digital picture of the manufacturing system, creation of data orchestration, ensuring data safety and short latency, creation of a human-centric framework, development of a predictive analytics tool to estimate uncertain parameters, creation of self-adaptive data-driven mechanisms and architecture in each digital twin, development of decision-aided algorithms for robust and agile planning and development for an AI-based controller actuation and reactive decision for real-time controls.